Hello, welcome to physics class. My name is Olujimi Gabriel. Today we'll be talking about center of gravity. Last time we talked about the moment of force. Now here is the continuation of that topic. But before we continue, here are the corrections to previous assignment. We are supposed to find the value of F2. Now, this is our point. We take our moment about this point. You indicate your clockwise and anti-clockwise moment. These are our clockwise and these two are the anti-clockwise moment. Now our clockwise moment equals to F times 4, and we know from the principle of moment, sum of clockwise moment equals to sum of anti-clockwise moment. And what is our anti-clockwise moment? This is 3 Newton force. The distance is 6 meters. And this is 2 Newton force. The distance from the point of action is 2 meters. Now, 2 times 2, that is the moment of the first force. Then 3 times 6. This is your answer. Our F equals to 22 divided by 4, which is equals to 5.5 Newton. Second example, you have to find the value of F. This is the point of action. You take your moment about that point. This is clockwise and this is anti-clockwise. Now, taking moment about that point, we have 5 times 0.05, which is our clockwise moment, and F times 0.25, which is the anti-clockwise moment, as you can see. Now, making F, so the formula, we have 5 times 0.5, which will be 2.5, divided by 0.25. The answer will be 10 Newton. And the last assignment, figure below, show a balance beam, calculate the unknown forces X and Y. These are X and Y. Now, this is the point. We take our moment about that point. That is clockwise moment equals to anti-clockwise moment. Now, our clockwise moment equals to 400 times 2.5. And our anti-clockwise moment equals to X times 1. Now, X equals to 1000. To find the value of Y, from the second condition of moment, we know that sum of upward forces equals to sum of downward forces. That is why we have something here. You can see Y equals to X plus 40. This is upward forces and this is what? Downward forces. That is X plus 400, which is equals to 1400 Newton. That is that on how to calculate forces acting on a beam in equilibrium. Now today we move to center of gravity. Center of gravity. You know, let's take for instance a stone or a plank of wood, for example. This stone contains many particles that made up this stone. Each weight of the stone, each weight of the particle is the sum total that made up the stone itself, as you can see in this diagram. Now, all these particles that has weight W1 up to W8, as many as you can have them in a matter. Now, they have a common point through which they act out, which we have as what? W. That point is called the center of gravity. Now, look at the center of gravity of a body is defined as the point through which the line of action of the weight of the body always passes, irrespective of the position of the body. Now, it is also the point at which the entire weight of the body appear to be concentrated. Now, look at the weight 1, 2, 3, 4, 5, 6, up to 8. All the weight appear to be concentrated as this center G, which we now call the weight of the body. That point is what we call the center of gravity. Now, another one is center of mass. The center of mass of the body is defined as the point at which the total mass of the body appears to be concentrated. The center of mass coincides with center of gravity for small objects. Just like what we have for center of gravity is the same for center of mass. Now, the position of center of gravity, when you see CG, it means center of gravity of regular uniform body. Now, look at this diagram. You can see the beam is balanced when we have mass M1 and mass M2 seated on it from both ends. The point at which the beam is balanced, we call it center of gravity. It may be that at that point is the weight of the beam, but there are some that are non-uniform. That is, when you say a uniform beam, it means the weight is always at the center. But there are some, their weight is not at the center. It can be found anywhere since they are non-uniform. But now we'll be looking at uniform bodies that have center of gravity at the middle. Now, a uniform rod has its center of gravity at the midpoint G of the length of the rod. The weight of the rod acts through G. That is, it acts through the center of gravity. That is when you are using a beam. Example of this is a seesaw or a lever. Now, the center of gravity of uniform circular plate is at its center. Look at it, it's uniform. Unlike the one that we saw before, this one is uniform. Circular disc. It should be plate. Now, the center of gravity is at the center of the plate, just like we are for the rod. Now, the center of gravity of a uniform circular ring is also at the center. Look at this, it's a complete plate, but when this side is being cut off, the center of gravity is still at the center. Another one is the center of gravity of a uniform square or rectangular sheet is at the midpoint of intersection of its diagonal. To get the center of gravity of any square or rectangular sheet, you get a diagonal. Where they intersect is where you have G. That is where the weight of the body is acting through. Now, the center of gravity of uniform triangular plate is at the center of the median. Now, when you trace this one down to bisect BC into 2, bisect AB into 2, bisect AC into 2, the center where they meet is the center of gravity. You can see the center of gravity is far away from A. It's closer to Y than A. That is why we say AG equals to 2/3 of AY. As you can see, that is that on that. Now, we move to the next. Now we move to stability of an object. The stability of an object. Now, there are 3 types of equilibrium. We have 1, stable equilibrium, unstable equilibrium, and neutral equilibrium. Now, look at a stable equilibrium. A body is said to be in stable equilibrium if it tends to return to its original position when slightly displaced. Now, look at, when you have a cone this way, standing on its base, the center of gravity is at this point. This is the weight, and this is the reaction on the surface of the base. Now, when you displace it, when you slightly displace this cone, look at, the center of gravity will still be within the base. Therefore, when released, it will fall back to its original position. Now, generally, a low center of gravity and wide base will help an object be in stable equilibrium. Now, look at, this base is wide and the cone is resting on the base. When it is slightly displaced, like I've explained before, you can see that the line of action will still be between the radius of the base. Therefore, when it is being released, it will fall back to its original position. Now, example of stable equilibrium is a cone resting on its base, a racing car with low center of gravity and wide base. 2. A sphere rolling on a horizontal plane. But this one can also be classified as neutral equilibrium because the center of gravity, the position of center of gravity do not change. But you can see this one, this position of G, here is low, here is high. But because the line of action is still within the radius of the base, it will fall back to its original position. Now we have unstable equilibrium. A body is said to be in an unstable equilibrium if, when slightly displaced, it tends to move further away from its original position. Look at this cone now. If you are able to manage to stand it on its apex, when you leave it, because the center of gravity is higher, when slightly displaced, it will move further away from its original position. Example of unstable equilibrium is a cone or an egg resting on its apex. There is no way this cone will stand because it's in an unstable equilibrium. Also, a ball that is rolling on an inverted bowl can never be stable. And a tight rope walker, just like those people that are walking on a tiny rope, there is no way they can be stable because they are in an unstable equilibrium. Now we have neutral equilibrium. A body is said to be in neutral equilibrium if, when slightly displaced, it tends to come to rest in a new position. Now look at this. Just like a rolling ball, this is where the center of gravity is. The position of that G does not change. Therefore, such object is said to be in neutral equilibrium, unlike the ones we have been talking about before. When a cylinder or cone is displaced to another, the position of the center of gravity and newt I above the horizontal surface remain unchanged. That is, the position of G remain unchanged after it has been displayed from its original position. Now, effect of height of center of gravity on stability of an object. The height of the center of gravity of a body above the ground level and the width of the object affect the stability of the object. Now, look at this shape. When the center of gravity is here, you can see when it is slightly displaced, in as much as the line of action is still within the radius of the base, this object will fall back to its original position. But when the center of gravity is high enough such that the line of action is outside the radius of the base, the object will fall off. That is the effect of height of center of gravity on stability of an object. That is, when center of gravity is high, the object can never be stable. It may fall off, just like a racing car when they are racing at a bend at a very high speed. Now, thus, a wide base and low center of gravity made for the stability of a body. It is for this reason that a racing car are built low and with wide wheelbase to prevent overturning at high speed around bend. If you have the luxury of watching Formula 1, you see those cars, they are so low and their tire base is very wide. The reason is to prevent overturning of the car when speeding at around a bend. Now, a car engine always located at the bottom of the car and not the roof. Now, imagine if the engine of the car is at the top. Just imagine what could happen when the car is racing at a very high speed. For this reason, when the center of gravity is low and with wide width, the object is said to be in stable equilibrium. Example: a non-uniform rod XY of mass 40 kg and length 5 meters lies on horizontal ground. Its center of gravity is 2.0 meters from end X. Calculate the vertical force P that will just be sufficient to lift the end Y from the ground. Now, look at, this is the non-uniform rod XY. Now, it's non-uniform. If it were to be a uniform rod, the mass of the rod would have been at the center. If the length is 5 meters, then the weight or the mass would have been 2.5 meter midway. But because it's a non-uniform, the center of gravity is at 2 meters from X. That's why you have the weight here. You have the weight here. Now, that means it's on the ground. Now, we are looking for a force that will just be sufficient enough to lift it up from this end. This point will now be our pivot because we are lifting it at one end. Now, you just take your moment about this point, which is X. Take your moment about this point. Now, this one forms our clockwise moment and this is anti-clockwise moment. Now, our clockwise moment equals to 4 times 10 times 2 because we are converting kilogram to Newton. That is why I have to multiply 10. Equals to our anti-clockwise moment. Equals to anti-clockwise moment. That is, from here to here is 5. That means here should be 5 and not 3. 5. Now, P equals to 4 times 10 times 2. That is 800 divided by 5 equals to 160. This place should be 800 and not 80. Now, our P equals to 160 Newton. Now, example 2. A meter rule is found to be balanced at 51 centimeter mark. When a body of mass 70 grams is suspended at 10 centimeter mark, The balance point is found to be at 25 centimeter. Find the mass of the meter rule. Now, a uniform meter rule, the mass is always at 50 because 1 meter, a meter rule is 1 meter, which is 100 centimeter. Now, midway should be 50 centimeter, but here it is 51 centimeter, you can see. Now, it has been balanced at 25 centimeter. From here to here is 51. Then you have to find this place, that is 26. From here to here is 25. 25. So this place will now be what? 15. You can see how to find all your distances. You have to locate the distance of this 70 gram from this pivot to where it is situated. Now, taking moment about P, M times bracket 51 minus 25, equals to 25 minus 10. That is M times 26 equals to 70 times 15. M equals to 70 times 15 divided by 26. The mass of the meter rule is 40.38 kilogram. 40.38 kilogram. This one should be 15, 26 and 15 and not 25 minus. Now, again, calculate the distance of the balance point from 0 and if the body was removed to 20 centimeter. Now, look at here. It was on 10 centimeter. It's now been moved to 20 centimeter. What is now the new balance point? What is the new balance point? Now, what we have here is this. From here to here is 25. We want to get the new balance point, that is the position of this pivot. Now, from end A to the midpoint is 51. And from here to here, we use Y to represent it. That means here will be 51 minus Y. Now, from here to here is Y. Then we find the distance between the 70 kilogram and the new balance point, which is Y minus 20. Now, taking moment about this point, 70 times the distance here, which is Y minus 20. You can see it here. That is anti-clockwise movement. Then your clockwise movement, which is M times this distance, which is this. And don't forget our M was 40.38. Open the bracket. When you do the algebra, you have Y equals to 31.32 centimeter. That is the new balance point when the body was moved to 20 centimeter mark. Now, assignment. A plan AB 3 meter long, weigh 20 kilogram, with its center of gravity 2 meters from end A, carry a load of mass 10 kilogram at the end A. It rests on 2 supports at C and D, which are 2 meters apart. Calculate the reaction at C and D. How far from D and on which side must a 24 kilogram be placed on the plan so as to make the reaction equal? Summary. The center of gravity is the point at which the entire weight of a body appear to be concentrated. A body is said to be in stable equilibrium when it tends to return to its original position when slightly displaced. A body is in an unstable equilibrium when slightly displaced, move further away from its original position. A body is in neutral equilibrium when it is slightly displaced. It's come to rest in its new position. For further reading, you can take any physics textbook to get more exercise and more knowledge on the topic moment of force. Till I come your way next time, thank you for your time and enjoy the rest of the day.